Hello and welcome to this tutorial from Escape Studios on procedurally shattering a mesh in Houdini. The effect we're trying to recreate is kind of similar to if you watch Game of Thrones when a White Walker is killed with a Dragonglass sword. So what we're starting off with is a basic animation, bad animation, of a base mesh of a person and a sword colliding with the mesh. And what we want to do is, from the point of impact on the sword, we want to shatter this mesh and turn it into kind of glass, which then can be turned into a particle system, so that you get the same kind of effect of the glass kind of exploding and blowing away and this mesh disintegrating. So if I hide those, jump into our Shatter setup. So this is the same thing again. We've just got the base mesh and also the sword. So what we want to start by doing is thinking about how we could go about trying to create this effect. So on the mesh, what we could do is we could scatter a load of points, and also on the sword we could scatter points, and then through transferring attributes we can detect where, based on distance, the sword is compared to the human mesh. You could actually do this through rigid bodies, but I thought, and kind of Voronoi factoring, but I thought it would be to create the kind of level of detail that you'd want. It would be a pretty big sim because you'd have a lot of geometry. So I thought we could do it with particles instead. But a lot of the principles and techniques that you'll learn in this can apply to different scenarios, and they're just kind of cool things to know. So anyway, let's start by dropping a scatter node here. See that? So there we go. Let's turn the total count up to 10,000. And we want to turn our primitive number attribute on, and also our primitive UVW attribute on as well. This will come in useful later on when we start instancing, and also because it's a deforming mesh, it needs to have the primitive number attribute, because frame by frame, otherwise the number of the points, the point IDs would change. But anyway, so we have our scatter node here for the mesh, and now for our sword as well, we'll drop down another scatter here. This doesn't need to be as dense with points. It only needs to be a rough estimation of the position of the sword, so we can maybe turn this to 10 or 20. Doesn't really matter. So yeah, I mean, this effect you want to happen pretty quickly. If you've seen the show, it kind of happens within a second or two. But again, it's not going to be absolutely perfect, but hopefully you might learn a few techniques that you can use in kind of different scenarios. So anyway, with the base mesh, we need to give these points attributes so that we can detect when a point is near to the sword, and we can give that point an attribute. So let's drop down a point wrangle node so that we can give this point an attribute, and we'll call this float f at merge equals set 0. Cool. We'll use a bit of vex in this tutorial, nothing too extreme. I mean, I'm no expert, but if you know a bit of coding, then that will help. And once you get your head around vex, it's quite a straightforward language. And then we want to drop another point wrangle node into this scatter node, and this we can call f at initialize and give this a value of 1. Okay, cool. So stopping there. Okay, so one thing we need to do, as I mentioned previously, is that this is a deforming mesh. The points are changing, and so we need to tell Houdini to interpolate the position of these points on a per frame basis. So if we drop an attribute interpolate node, okay, and the first input of this we want to plug our scatter node into. The second input we want to plug our mesh into. And then we have these source prim UV attributes, which are important, again, for letting Houdini know that these points are the same frame to frame. Okay, so we have our attributes ready. Now we need to drop a solver in. And what the solver does is this is what's going to calculate every frame how much the collision attribute is spreading, so we can control how fast or slow we want the collision attribute to spread throughout the mesh. So we plug our two point wrangle nodes in there, and if we look at these point wrangles, you can see now point attributes. We have P, so position of the point, and also the initialize attribute which we've added, and there you have the merge attribute which we've added. So if we jump into our solver, so what we need here, we need to copy our attributes from these point wrangle nodes. So we can get attribute copy. We don't want to match P. And also we don't want to copy our color attribute. So our first input of the attribute copy is going to go into our first input, which is this point wrangle. And our second input of the attribute copy is going to go to previous frame. Now, instead of writing vex for this, I'm going to use a technique I've seen where we use an attribute VOP. It's you know, it is vex essentially, but it's a visual way of understanding what's going on. So we'll drop down an attribute VOP here, plug our attribute copy into the first input, and then our input 2, which is our second point wrangle, into the second input of the attribute VOP. Okay. Let's jump inside there. Okay, so we've got our VOP globals and our VOP outputs. We don't need the outputs because we're going to create our own. So we need to first create point clouds from these. So PC open, point cloud open. We need 2 of those for our 2 different attributes. So P goes to P, 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 and file op input 1, file op input 2. Okay. Stopping there. Okay, so we need to drop in a couple of filters. Oops. Connected that to the wrong input, so I'll change that. So we need a filter here, two of those. One for our merge attribute and one for our initialize attribute. So the top filter we want to change from vector to float and put the channel as merge. This again change from vector to float, and this is our initialize. So from these two filters we can select the appropriate channel, and now we want to add them together, because remember this is happening every frame, and so every frame it's adding together and it's adding the attribute so that you get that kind of propagation across the mesh, across the points. So we want to add these two values together, and then we also want to bind this to add the bound value on merge as well. So we want to then clamp this from a value of between 0 and 1. Excellent. And then we want to export this back to the merge attribute which we created. Okay. So what we want to be able to do is visualize in the viewport this attribute spreading throughout our points. And so one way to do that would be to color the points based on the value of that attribute. So points which have the attribute propagated to them could be red, and points without the attribute or a value of 0 would be black. So one way we could do that is by writing a couple of lines of vex again. Run over points. Okay, so at CD, so each point color value we want to set to a value of 1, 0, 0, or red, RGB 1, 0, 0. And now we want to set the red channel of each point equal to its merge value. And so if a point has a merge value of greater than 0, obviously it will start to turn red. But we want to be able to control how long the point exists for, so that we can limit the amount of particles which are emit from each point and reduce the kind of overall size of the simulation. So one way we could do that is just drop in a delete node, and we want to run over the points again and delete by the expression, and the expression will be at merge equal to 1. And so between 0 and 1, as I said, the point will be able to emit particles, but as soon as it hits a value of 1, then the point will be deleted. And so if we look at in the viewport how it is just with the color values, you can see how quickly the attribute spreads. And obviously the speed of this can be controlled through your solver by increasing the substeps. Obviously this makes the simulation run slower because there's more calculations being performed, but it speeds up the rate at which the attribute is propagated because each point is looking 5 times a frame instead of just 1. But I'm quite happy with it at 1 for the purposes of this tutorial, so that we can keep things sped up. Okay, so now if we look at our delete node, we should see that as particles start to turn more red, they'll be deleted. There you go. As the attribute spreads, the particles get deleted. Excellent. That works perfectly. Okay. So what we want to do now is, so that we can emit from the initial mesh that we have, we want to be able to transfer these color values across to the mesh, and from that we can emit the particles. So if we have an attribute transfer, connect that to there, connect the first input to the original mesh. If we look at that node, you can see we've got color values, the source group, destiny points, and now we should, there you go, you get the propagating, but I want to initialize this mesh with just a black color, so we want 0, 0, 0. Stopping that. Okay, so what we want to do now is we want to transfer the color values from each point to the original mesh. And so one way we can do this is by dropping an attribute transfer node. And we want to plug the second input into our points and the first input into our mesh. And I just want to initialize the mesh with just a black color, just to make things easier to see. So attribute, I'm going to create an attribute, call this CD color, and it's a vector. Let's just double check that. Cool. So every frame, the red attribute is going to be transferred to the mesh, and so we should get the red spreading throughout our mesh, which we can then emit the particles from. So if we look, because we're transferring the attribute based on distance, okay, so one of the things we'll want to have a play around with is the conditions. The distance threshold is obviously how far away the point has to be from what you want to transfer the attribute to be able to actually transfer. 10's quite high, and so that's why we're getting quite a strange banding effect. So let's drop that down to 1. And the blend width, again, is going to affect how the color spreads. So if we press play now, so we're getting that kind of dissolving effect, which is what we want. Maybe drop this value down a tiny bit more. There you go. And it's kind of spreading across the mesh quite nicely. Okay, so now we can start to think about how we would more particles and more dynamics. So one thing we need to do is compute the velocity of each point, and this is calculated again per frame based on a value, the position of the point on one frame compared to the other. And this is going to be useful for affecting how the particles move when they're born. So result type, we want to do compute velocity and angular velocity. So now you see we have 2 more attributes, V and W. So we have 7 point attributes. And so, let's turn that off. Okay. So now we've got the velocity of the points. We can affect how the particles are spinning and rotating when they're born. And so we want to adjust this W, which is our angular velocity attribute. So if we put in an attribute wrangle, let's give it a value of, say, 10. So at W equals set 10 on the X, 10 on the Y, 0. Okay. Now, let's pop in a pop network. Jump into that. And so you'll see it's creating particles on the surface already. So let's jump into this network. At the moment we don't have any gravity, but we'll add that in. We have our mesh here, and we want to change a few things about how the particles are emit from this mesh. So if we go to our pop source node, use first context geometry. Okay. So our emission attribute, because we want to emit only from areas which are red, we can use our emission attribute CD, so color. And we want to scale our point count by area. So let's just take a quick look at this. It's going to look a bit strange, I think, but there you go. It's quite a nice effect, but again, there's no gravity, so the particles are just sitting there, and you can see already it's starting to slow down because we've got 22,000 points. So let's add in some gravity. Play through this again. Okay, that's better. So you can see the particles are inheriting the velocity of the mesh, and that's what that trail and angular velocity have done. So it creates a more kind of realistic effect as this mesh moves. The particles move at the same force as well. Okay, so now let's look at how our constant birth rate of 5,000, let's just put that to 1,000 to begin, just to keep things speedy. Get rid of that. We want to add a force to this, the particles. So let's add a pop force in. And we want these particles to spray kind of around the back as this guy turns around. So let's give a -5 force and a -5 force again. Okay, so now if we play, looks better. It looks better than it was before, but we can add some noise into this to get a bit more chaos in the movement of the particles. So let's stick this actually just up to 10, just so that we can see what the effect is. Okay. And maybe put our swirl size up to 5. Again, this is going to look unrealistic, but just so that we can kind of see what's happening, what that value change does. One thing I'm going to do is add in a ground plane, just so that we have something to collide with on the ground. So let's play that through. So the amplitude is quite nice. I think if we look at the geometry spreadsheet, go to our pop object, geometry, as we play this through, there you go, you start to see some points. You have the normal velocity, and we've got our torque, our angular velocity value here. So to use that, we can add a pop torque node and turn the amount to 0, so that we're using the angular velocity value. And now let's maybe in our source, if we maybe add to the inherited velocity, see what happens. Maybe a value of -1, -1, and have no variance on that. You can spend hours playing with values, but again, I'm not going to get it perfect. I'll just try and get the effect. And so one thing you might notice is that these particles are spreading out loads. And so what we can do is we can change their physical properties to increase the friction on the ground. Let's have 0.5 friction. Play that again. Okay, and also decrease the bounce. And you're getting less movement on the ground. You're still getting quite a lot, but in a way it kind of looks quite cool. Maybe bring that down a bit more, put the friction up. Play again. Starting to look a bit kind of fluid. Okay, that's better. I mean, we are going to instance geometry to these points anyway. So what we can do now, is if we hop up, I'm just going to drop in a null just to rename this out particles. What we're going to do now is we're going to go back up to object level, and we're going to instance some geometry to these particles. So you can see here I've got 4 fragments. Let's focus in on these. And all these are, it was a cube that I fractured, and yeah, just to create some kind of shard shapes. And what we want to do is we want to, for each particle, we want to instance one of these fragments, and we also want to be able to vary certain things. like the scale in the all three axis, and yeah, just to vary it up so that they don't all look exactly the same. So we can do that by dropping, if we hide these, an instance node. And again, this these principles can be applied to anything. Instancing is a really powerful way of generating a lot of geometry without using a huge amount of memory, because obviously it's referencing only one geometry node as opposed to creating all the geometry separately. So we have our instance node. Let's call this instance fragments. And now if we jump into our instance node, it'll give us an add node. We're not going to be using that. It just creates a point at the origin because we're going to be using our particles. So if we go to merge, object merge, transform into this object, and let's find our, export the relative path, our particles, out particles. And if we just go and hide this ground plane so that we're not seeing it twice, go into our instance fragments. Okay, so what we want to do is every particle give a different value, a different scale value, so that, as I said before, it varies up the look of the simulation. So let's drop in a attribute wrangle. Okay, run over points. Okay, so we want to create an attribute wrangle so that we can go over the points. And firstly, we want to create a variable for the p-scale, which is quite an important attribute for particles. And it's going to control the overall size of the instance. So we want to set the p-scale to between fit 01, a random number, and use point num, the point number as the seed, and we want it to be, say, between the values 0.1, 0.3, or we could even say channel, call it scale min, and channel scale max. Okay, and so if we click there, I missed out a bracket. We now have these, so let's set our scale min to 0.1 and our maximum scale to 0.3. Okay, and so we want to create a attribute p-scale, which is a float, and we want to set the value between, which is fit 01, a random number, and we're using the point number as the seed, and then we can create channels, and we'll call this scale min, and another channel scale max. And we're missing a bracket there. Okay. Okay. If we have too many parameters, these are ones that I created earlier, we can just go into the parameter interface and delete the parameters that we don't need. Okay. So now the p scale of each particle is driven by this variable, or this value, sorry. So we say 0.1 and 0.3. And it's going to be a random number for each between these values. So now if we want to vary the size in all three axes, we need to create some variables. So let's start with a float. Let's call it random x equals fit01 rand. Same again, pt num, that's the seed, and then between 0.1 and 0.5. Okay, and then we'll do exactly the same for random y and random z. And then we'll create a variable called scale using these three values. Okay, so at the moment we have these variables, but we don't actually have, we're not telling each particle the instance geometry to use. So let's just write a comment up here to say set random p scale and scale. And now we want to vary instance geometry randomly. So the attribute which controls the instance number, we are going to use integer at instance num, and we want to set it to, again, fit01 random number between, using the point number as a seed, 0 and 4, because that's the amount of different fragments we have. But because this might turn in a value, well, a float value, and we need an integer, we want to add ceiling, so it's going to round the value up or down. And so we'll only get integer values. And now we have the value, we need to point that particle to that particular fragment. So we want to create a string, and the attribute which controls the instance is called instance. And now to kind of concatenate the instance number and the instance string, the path to the geometry, we can use sprintf, sprintf, and it's /obj object, and then if we hop back up, we can see fragment underscore is what we need to use. So we'll go obj underscore fragment fragment underscore, and then to insert the number, to format the number, we want %d, and then we can put a comma, and we do at instance num. And now if we check the values are correct, if we show the human and we rotate round, I forgot to say turn on fast point instancing. You can see we're starting to emit that geometry, and you can see it's varying quite nicely, and we get nice rotations because we added the angular velocity to the points. And so maybe if I change the background color, let's go to dark, save that. So that looks quite nice. I mean, I'm not going to bump up the values too much, and the mesh, one way you could do it is to comp, is you could render out a pass based on the red value, and so you could dissolve the original person in the shot based on using the red value as a matte, and then it would dissolve at the same time as the particles were being emitted. So we could maybe jump and make these a bit bigger, say between 0.1 and 0.4. Let's run that simulation again. And it does run quite quickly because we're only referencing this geometry. We're not trying to, create all these points individually as it would be if we were doing a rigid body simulation and we were fracturing this, entire mesh. You might get a kind of more accurate result, and it might be easier, but at the same time, this has produced quite a good result, and the simulation is pretty much instant. And so, yeah, that's pretty much it. I hope you've kind of learned something from this. Again, as I said, the principles can be applied to anything. It's instancing is really powerful, and also being able to control the spread of an attribute in Houdini can also come in really, really handy. It kind of took me a while to figure out how best to spread attributes, but I think this is a pretty accurate way, and you can produce some pretty cool results from it. So I hope you've enjoyed it, and look forward to seeing you again. Thanks.